Hello and welcome to another walkthrough. Now this time it will be Edexcel IAL Physics Unit 1, May 2025, which I have never seen before. So this is going to be a blind solve for the entire paper under the real exam conditions. So along the walkthrough, I might be making mistakes, which I'll correct if I realize in the walkthrough. But if I don't, I'll annotate the video and I'll try to explain the worked solution and the thought process as simply as possible. At the end of the walkthrough, I'll mark the paper anyway. So this walkthrough is not meant to just show you the destination of the solutions, but also show you the journey to the destination. If you feel like jumping to a particular question, you can use chapters in the description. Otherwise, stick around. You might be getting some tips along the way. If you are ready, I'll see you in there. Okay, so here's the paper, and I'm going to start the timer now. Alright, let's go. So let's do the multiple choice first, right? So I'm just going to keep the question on the left part here, and maybe I'm going to zoom in to the working area here. Now we have what? Number 1, a cube of volume V is placed in a liquid of density rho. The cube displaces a weight W of the liquid. Which of the following gives the magnitude of the upthrust acting on the cube? Right. So, well, it's probably floating, right? So we have the volume V is placed in liquid, so the cube displaces the weight W of the liquid, displaces the weight W, so that would be the weight of that would be equal to the force of the upthrust, because upthrust is the weight displaced, is the weight of the liquid displaced by the object. So I'm just going to go with D actually. I mean, if you understand the concept there's no need to do math, right? Okay. Yeah. Is that right? The cube displaces a weight of W of the liquid. Just checking. Yeah, because if we use V times rho here, it wouldn't be right, because V is the whole volume of the cube. Maybe it doesn't sink entirely, right? So we have to do W here. All right, just checking. Number 2, a seesaw is a uniform beam that balances on a support. The beam can rotate around the top of the support. Okay. 2 children of equal weight sit on seesaw and equal distance from support. That makes sense. Which row of the table describes the resultant force of the result and the resultant moment on the beam? The resultant force on the beam, right? The resultant force on the beam should be 0 because the beam is not moving up or down. The resultant moment on the beam should also be 0 because it doesn't rotate anyway, right? So that should be A. It's just equilibrium concept there, guys. Number 3, the diagram shows a ball of mass m moving at a speed v along the horizontal table. The ball leaves the table in time. The time taken between the ball leaving the table and landing is t. So it's like, like that path takes time t. Yeah. The second ball of mass 2m moves at a speed 2v along the table. Which of the following gives the time taken between the second ball leaving the table and landing on the floor? Right. So it tells you that if you go with the speed v with mass m, it's going to take time t. So the difference here is just the mass and the speed. Well, because we are assuming that there is no air resistance, right? Or if there is, then it should be the same way here. So when you consider the trajectory of a projectile, the time taken from the object to go from one point to another in the projectile, in this case, would depend on the height, right? Because the time taken here, I mean, if you do vertical, it would just be s equals ut plus half at squared, that would be the vertical. Now, because initially the vertical speed is 0 and the height is fixed here, so this s here is the height, it is fixed. So that means the time taken if we make that the subject, right, so it would be t equals 2s over a and then square root that. Just rearranging that. So you see time depends on the height, which is the same, and the acceleration in this case would be the acceleration due to gravity, which is also the same. So it should take the same time regardless of the mass and the initial speed, because the initial speed is along the horizontal. It doesn't affect the u here because in this case u in this term is 0 anyway. So I'm just going to go with t here, yeah? Okay. All right. And then number 4. The force acting on a person sitting on a chair are weight and normal contact force. Yeah, sitting on a chair, so a person sitting on a chair there. Weight, so we have a weight here and a normal force. Okay. Which of the following gives a reason why these forces do not form a Newton's third law? Well, Newton's third law requires that you must have force acting on different bodies. Yeah, this is the same body, right? These two forces are not Newton's third law pair because they are on the same body. Okay, do we have that already? Because the forces act on the same body. Yeah, so that's C. And the other requirements would be forces of the same type. If it's mechanical force, it should be mechanical force. If it's gravitational, it should be the same. If it's electrostatic, then it should be the same. These are like normal reaction and weight are not the same type either, but it doesn't have in the choice, right? Weight is due to the earth, gravity. But normal reaction is like a mechanical force pushing up by the chair. Yeah, it's a contact force. But yeah, because it doesn't have it here, so I'm gonna go with because the forces act on the same object. Give a reason why they do not, right? They do not form Newton's third law because they act on the same body. But actually they shouldn't. If they were to follow the Newton's third law, then they shouldn't act on the same body. Okay, number 5. A wire is used to hang a picture from a hook on the wall. The wire exerts force T1, T2 on the picture. The pictures has weight W. Okay, which of the following describe the relationship between the forces when the picture is hanging on the wall? Because it is hanging in equilibrium, assumingly, so that means these, wait, hang on, the picture has a weight of that. What kind of, oh, okay, this is from the back of the, probably from the back of the picture, and yeah. So, tension, T1, T2, acts on the picture. W also acts on the picture. So that means these forces on the picture must add up to 0. Okay, so W plus T1 plus T2 should be 0. Now we just look at the options here, which one matches, like this equation. So I can rearrange the equation. Well, B is already the right one, but let's check the other ones anyway, just in case. Well, if I move T1 and T2 to the other side, I wouldn't get a positive T1 here. That would be wrong. This one wouldn't be right because it contradicts B anyway, so we're going to go for B. Okay, that would be my answer there. Number 6, an object has a constant non-zero acceleration. Which of the following displacement time graphs could represent the motion of the object? Well, constant non-zero acceleration, right? So that means if we draw a VT graph first, well, it might be a good idea to just go step by step. So if we draw a VT graph, a constant acceleration would give something like this. Depending on the initial speed, that would be the velocity time graph. It's going to go linear, right? Because the gradient, which is the acceleration, is a constant value, which is a linear equation there. Now, if you go further to displacement from velocity, or st, it's going to go parabolic. Because you would have to, mathematically speaking, you would have to integrate the VT graph to get the DT graph. So integrating a linear function, you get a parabolic like that. All right, so it should look like a parabolic. But I don't have it here. Oh, okay. All right. Displacement time graph could represent the motion of the object. Let's see. Forgot. Because the acceleration could be negative. So if we have another case where it's negative, yeah, this is a positive, this is a negative, right? So it would look like, so if we have, yeah, it would be like this, right? Would be the opposite way. So the only one that makes sense should be choice B here, because it go parabolic at first and the gradient decreases. That means the velocity decreases because we have a negative acceleration. So B is the best one, I would say. I'm just going to go with B. Okay, number 7. The force acting on the helicopter are shown. All right, the helicopter is represented by the dot. Okay, so there's a pulling force to the right as well. Which of the following expression gives the magnitude of resultant force? Well, you can do, so in order to find the resultant force, you just sum up the vertical and the horizontal components first. Here we have 2 vertical components, like 2 vertical forces. We have to sum them up. So if we sum them up, you're going to have, that would be 15,000 minus that, right? Because 15,000 is greater. And then because looking at the options, it doesn't require that you do the math totally. You just plug in, you just like show the arithmetic there, what would give the answer. So we're just going to do that. And then we would square this, right? Plus this squared. And then we would square root that because we're doing Pythagoras on the vertical and the horizontal separately there. And then that would match option B, wouldn't it? Yeah, because we need to square root as well. I'm just checking. Wait, hang on. What's the difference? Okay. So, no, it's not B. Gotta be careful there. We have to subtract first and then square later. So that should be D. Okay. Almost flopped there. Question 8. A box of weight W slides down a ramp. The ramp is at an angle theta. The horizontal frictional force F acting on the box is shown. Which of the following is correct when the box moves at a constant speed? Well, constant speed is the keyword here because when we have that, that means the resultant force is 0. Okay? Constant speed down. Resultant force 0, right? Well, that means if we do the component here, well, you have to know when we have an inclined plane like that, this is almost always W sine theta. Yeah, and that is W cos theta. But because we already know that this is constant speed, so we're just going to say that F should be equal to W sine theta. Yeah, there is no other pulling force, so that would be it because, well, we have another force here, which is the normal reaction, but we don't care about it because it doesn't have anything about N here. We just care about the F. We want the friction. So friction should be W sine theta. Okay? Because it's at a constant speed. So what is that? This one, right? Yeah. Okay, so that's it. Number 9. The driver of a car applies the brakes. The frictional force F between the tires and the road is constant. Okay. The average power dissipated by F is 50 kilowatts. The car moves at a distance of 13 in time that before coming to rest. Which of the following expression gives F? Well, basically this is, well, we can do work done equals change in kinetic energy, right? Or we can find the acceleration and then find the, do F equals ma, right? So, well, let's do the latter one because that might be easier for you guys. So we have distance 13 meters with time of that coming to rest. So this is S, this is T, this is coming to rest. So coming to rest, V equals 0, right? And we can do the S equals VT minus half AT squared just to find A. Yeah, just to find A. So we do 13 equals, V is 0, so that's minus 1/2. A is going to be negative. Yeah, we expect that, and this is 2.3 squared. Well, we're not going to solve it probably, maybe not. So we're just going to derive the math there. Well, in this case, because we don't deal with negative sign here because we're going to take it as a deceleration. Yeah, So I'm just going to do 13 times 2 divided by 2.3 squared. That would be the deceleration, all right? And then we're not done because we need to, the average power is that, wait, hang on. Oh, right. The average power is that. Well, then we got to find the average speed. Okay, we got to find the average speed. Okay, I think energy is easier now. Okay, I think energy is easier. Let's do energy. So KE lost equals work done against friction. So KE loss is half m, and this is the average. Wait, KE lost. Okay, you know what? We're gonna find the VAVG squared. Is that gonna work? Hang on. Oh, it should be initial. Yeah, should be initial. Equals average power dissipated by F, so that's F, and then the distance is 13. Okay, now U, right? Okay, so this distance here, S equals U plus V over 2 times T. Yeah, I guess I have to find U from there anyway. So we're going to find U from here. This is Suvat. You need to find the initial speed first because I'm going to plug it in the energy equation here, right? So S is 13 equals V is 0, so that's going to be just U over 2 times 2.3. So that's U is going to be 2 times 13 over 2.3. We're not going to do the math here. We're just going to plug in numbers. Yeah. And then, wait, that's average power. Average power is, so average power is FV. Or isn't that also F times, this V is the average, should be the average speed, so this is U plus V over 2. Okay? Right, sorry, no. This is actually easier. Sorry. Okay, I think I gotta do this again. Okay, so because I didn't read average power here. Okay, so average power is F times average speed, yeah? But we happen to know that average speed is just U plus V over 2. Yeah, that's the average speed. Okay? And I shouldn't have deleted that. Sorry for the confusion. The average speed, yeah, times time is going to be equal to the distance. So if we make U plus V over 2 the subject, we get 13 over 2.3. So this is the average speed. We plug it in here, we're going to find F, right? So if we plug it in, power is 50 times 10 to the 3 equals F times U plus V over 2 is 13 over 2.3. All right? Okay, so F equals 50 times 10 to the 3 times 2.3 divided by 13. And that would be the same as option A. Yeah. All right, just doing the math there, guys. Sorry about the confusion. Question 10. A toy train of mass 3m is moving with the speed v. Toy truck m, 2v, opposite direction. Train truck collide, move off together. So if we calculate the initial momentum of each one, this is 3mv, this is 2mv in their respective direction. So as you can see, the toy train has a greater momentum, so it should make the whole thing go to the right. The only thing that makes sense is that they together go to the right, right? So if we do conservation of linear momentum, so let's do rightward as positive. So we have 3mv from the train minus 2mv from the truck equals, because they both go to the right, so they stick together as 4m combined, yeah, and multiplied by some capital V. All right, so this is 1 mv equals 4m big V, and m cancel, so we have new speed, so V equals little v over 4. which is choice A. Okay, so that's it for this one. Well, you gotta make some sense first. Alright, now let's do the written part. More fun, I think. A resultant force of 4,800 Newton acts on the boat. The acceleration of the boat is 0.31. I'm just gonna keep the question on here. Okay. The acceleration of the boat is that. Calculate the weight. Okay. Yeah, okay, so we just find the mass first. Mass equals resultant force over acceleration, so that's just that, right? Divided by 0.31. And I'm just going to keep that because then the weight is just mass times gravitational acceleration. So I'm just going to wrap that up, divide by 0.131 and times 9.81. Okay? Just do everything all at once. I prefer like that, yeah? Divided by 0.31. Okay, so that's going to be the weight, which is quite a lot. Yeah, I'm just checking. Oh, I plugged in the wrong number there, guys. Gotta be careful there. Oh, come on. 4,800 divided by 0.31 times 9.81. Okay. That is 151,896.77, blah, blah, blah. So I'm just going to answer, well, probably 3 significant figures, I would say. 152,000 newtons, because that's the weight they want. Okay. Number 12. A person rides a bicycle along the path shown. At the end of the path, the magnitude of the displacement from the start is less than the distance traveled. Of course, describe why the displacement is less than the distance traveled by the person. Well, because, as you can see, yeah, the path shown is not a straight line, right? Because if it was, then they would be equal. The path shown, I'm just going to write, is not a straight line. Yeah. So the actual distance traveled is greater than the displacement. That would be how I go with that. Yeah, I mean, because it's curved, right? So you would need extra distance to travel. All right. I mean, being 2 marks here make me think the magnitude. Yeah, okay. Now, I probably have to say that and distance is a scalar quantity. So doesn't have a direction, but displacement is a vector. So a straight line drawn from the start directly to the end. So I mean, because we got to make sense that the displacement is a straight line first, because it doesn't say here. It only says displacement. So we cannot assume that the question already knows that displacement is a straight line. We got to say something about that first. So that would make this a perfect 2 marker. Okay. And then part B, the velocity time graph for the path of the bicycle ride is shown. Determine the maximum acceleration of the person on the bicycle. So the maximum acceleration would be the maximum gradient, because gradient is the acceleration. So I would say, wouldn't you say, this is the line of greatest slope? Yeah, so we're just going to do that to show that we acknowledge that the larger the triangle, usually the better the accuracy. So we're going to find the gradient on that one. So we do gradient m equals, so this is 5, right? So 5 minus, that's what? This is 1, so that would be 1.8, wouldn't it? Divided by what is this time here? This is so this would be 15, so that's 16 minus, yeah, this is what? That would be 4, right? Yeah, happy with that? So that would be 3.2 divided by 12. Well, let's do a calculator there. Okay. 3.2 divided by 12, yeah. So that is 0.266, blah, blah, blah. I'm just going to do 0.27 here, meters per second squared. Yeah, that's fine. Hang on. 0.27 meters per second squared would be the maximum acceleration from the graph. All right. Number 13. In a game of basketball, points are scored by throwing a ball so that it falls through a hoop. The rules state that the distance d between the hoop and the floor should be 3 meters. So that should be distance d. The basketball player throws the ball so that it falls through the hoop as shown. The ball was thrown from the height of 1.7 meters. Okay, so that is saying that this is 1.7. Okay, above the floor, the initial vertical component of the velocity of the ball is 5.1. So this is 5.1, but we don't know this, right? Okay, as the ball entered the hoop, the vertical component of the velocity of the ball was 2.1. And we need to know that it's going down. So it's going down like, maybe like this. Yeah, 2.1 with some some horizontal component there, which is kept the same as, let's say, u and u here, yeah? Okay. Deduce whether d was 3.0 meters. Okay, so, right, let me think about that for a bit. Okay. So what I have in mind right now is that we can use conservation of energy here. Yeah? Because look, from this point to this point, if we assume again negligible air resistance, well, although it doesn't say, but we should assume that because to make it accurate. So there is a height increase here, right? And because regarding energy, the horizontal component of speed doesn't change, so the kinetic energy due to the horizontal component doesn't change. So when we talk about energy conservation, energy transfer, it's just the vertical component of kinetic energy that converts to the GPE gain, right? So I'm just going to write here, if we assume that d equals 3.0 first, assuming d equals 3.0 meters, and then we do ke vertical, y, yeah, I'm just going to do y, ke y lost equals GPE gain, yeah? So energy conservation here, right? So that would be half m, and the initial vertical component is 5.1 squared here, yeah? Lost, we do subtraction because it's lost to that. Okay? It doesn't matter the direction. We can do, vertical component. As long as they are vertical, then we can do that. Okay. And then this must be equal to the mgh, which is the height gain. Now, if we assume that d is 3.0, then we can do, well, actually we can find the height, the change in height here. Let's find the change in height, the h, yeah? We can just solve this equation, right? So m cancel, let's see if it's, it should be what? What are we looking at? If it's true, then it should be about 1.3, right? The change in height there, okay? So is it true? Well, h equals, if you solve all that maths, it's just 1/2 5.1 squared minus 2.1 squared divided by the g value, which is 9.81. So I'm just going to plug in the whole thing there because I would like to do that. 5.1 squared minus 2.1 squared, and then divided by 9.81. Yeah, so that would be the way I go with that. And this is 1.100. So 1.1 is not 1.3, right? It's not equal to 1.3. Well, let's just be clear. 1.3 comes from, 3 minus 1.7, right? Because it's just 1.7 from the floor, so it's 1.3 to the hoop, yeah? So therefore, D is not 3. I mean, D should have been 1.7 plus, so D should be 1.7 plus 1.1, which is 2.8. So therefore, D is not 3. Bam. All right. Yeah, that's it. Number 14. We are at 30 now. The brakes in the car reduce the kinetic energy of the car. In an electric car, some of this energy is transferred to the battery. Okay. An electric car of mass 1800 kilograms moves at a speed of 14 uphill. The driver applies the brake to bring the car to a stop. During the braking, the vertical displacement of the car is 0.76. So this is uphill. So let's say it stops here. Yeah. So this is V equals 0. The vertical displacement. So if we draw from the center of mass there to the center of mass here, this distance is 0.76. Okay. And the energy stored in the battery increases by that. So we gotta figure out where this energy comes from. Reduce the kinetic energy of the car, okay? And in an electric car, some of this energy is transferred to the battery. Okay, so because it's only some, right? We gotta say change in kinetic energy first, yeah? So, all right, hang on. To a stop during the braking, the vertical displacement. Okay, so if we do KE loss again equals GPE gain, yeah, but there is some work done against friction. That's the typical equation there if you're going up, right? Just gonna put here, and this would be 1/2 times m times v squared equals GPE gain. So that would be m times g times h, which is the vertical displacement there, 0.76. Okay. And we now have the work done against friction here. It's this quantity here. So let's do the math to find the WF just in case, right? Okay, just find that first. All right, yeah. So that would be 1/2 times 1800 times 14 squared. And then I'm just going to do minus the other term already. 9.81 times 0.76. So we get a positive value indeed. Yeah, I'm just going to copy the whole number down. Okay, so that amount is the work done against friction. Now, so if you convert totally the kinetic energy to bring the car to a stop, there would be this amount of energy, right? That is like it might go to friction or something. So the whole kinetic energy will go to friction, and some of them will go to the battery, of course. Okay, so that means, I mean, this is the kinetic energy we have. Yeah. Now, because all of the, okay, let me draw the Sankey diagram. So Sankey diagram says that, well, you are bringing the car up, right? So the main thing, the main output would be the GPE gain. But then you're wasting your energy to something else as well, like friction, and also some other things, depending on how many, like the byproduct energies you have there. So this is the totality of this other types of energy apart from the main source of energy. We want GPE to be gained, right? And it's this amount. So the difference is this. That means this is like This can be thought of as the total input that the electric car, like the battery, can take, right? So that means the efficiency must be based on this value and not the total kinetic energy, because you have to remember that some kinetic energy must be converted to the GPE gain first. So the leftover, the remainder, would be the maximum possibility of the battery car that it can take. Yeah. So we're just going to do percentage efficiency here equals, well, the actual output, which is 45,000, is actually what battery gets. But then the total that it can get is just this guy. Yeah. So I'm just going to do equal first, and then I'm just going to do 55,000 divided by answer. Yeah, so that would be 0.276, blah, blah, blah. So it's just 27.6%. Yeah? All right, that would be my answer there. Number 15. Okay, a builder uses bricks to build a wall. As the wall gets taller, the force on the brick at the bottom of the wall increases. A force compression graph for this brick is shown. So this is, like Hooke's law. Determine the increase in elastic strain energy of the brick as the force increases from 85 to 140. So 85 newtons, we gotta be careful. So this is what? Per square, it's 10, right? So 60, 70, 80, 85 is around here. I gotta use maybe smaller. 85 around here. So that would be equivalent to this, right? Do we have a... let's do that. Okay, sorry. That would be... Yeah, we would have to do the other line as well, 140. So 140 is probably more accurately that. Ooh, but maybe the x value might be also halfway here. Now, what we need to do is that the increase in elastic strain energy would be just this area here, right? Because what's the definition of EPE stored in the what is this? The brick. So if you are stretching it at this point, this will be the energy stored. It's the area under the force extension graph. Yeah? Or if you prefer remembering the formula, it's EPE in the spring or something equals half Fx. But in this case, it's just the compression. So same thing. Yeah? But when you stretch to 140 newtons, it becomes this area. That means the increase would be the difference between those areas, and it is this very trapezium, right? So I'm just going to do change in EPE is just area of trapezium there, the trapezium I drew. So it's just 1/2. So that's, well, the two parallel sides would be easy because they tell us that it's from 85 to 140, so we just add them up, right? And then just increase the thickness, and then we multiply that by the change in, the compression here, and be careful, it's nanometer. So that is how many? This is 75. So this, hang on. 75, so that's 5 each, 60, 70, yeah. So this is 55, and this is 95, right? No, hang on, I'm confused now. Let's do, so it's per square is 5, right? So 1, 2, 3, 4, 5, 6, 7. So 7 times 5 is 35, yeah. And then there is half here and another half here, so it's 40. Okay, so 40 nanometer. Okay, is that right? Let me just do that again. Okay, 1, 2, 3, 4, 5, that would be 75. Another 25 would be that. Okay, 1, 2, 3, 4, 5, 6, 7, and then another 2 halves, so which is 8. 8 times 5 is 40. 40 nanometer, we multiply that by 10 to the minus 9 because we need SI units to make it joules. Yeah, force is already Newton, so we're fine. We're just gonna plug that in a calculator. So 1/2 times 85 plus 140 times 40 times 10 to the minus 9. Ooh, so that is 4.5 times, how many zero then? 1, 2, 3, 4, 5, 6, 10 to the minus 6, right? Yeah? Okay. I think I'm okay with all that. All right. So I'm just going to keep that answer. Yeah, it's a very tiny energy, of course, because it doesn't compress much, if you think about it, because it's nanometer. The brick undergoes elastic deformation. State what is meant by elastic deformation. Okay, so deformation in which Hooke's law, yeah, Hooke's law is still obeyed. Hooke's law is obeyed. Oh wait, hang on. Hang on, because I think elastic deformation would be relatable to elastic point. An elastic point is something else. I think is the deformation under which the material can return to its original shape when the load is released. Well, that is actually relatable to elastic point. So elastic point is the point under which the material returns to the original shape when the load is released. So I'm just gonna write deformation in which material is blah blah blah. All right. Now if it was plastic, then it's not the case. All right. Okay. Number 16. We have a student used the falling ball method to determine the viscosity of vegetable oil. He measured the diameter of the ball bearing. Okay, a little black dot there. He dropped the ball bearing into a measuring cylinder containing vegetable oil, as shown. The ball bearing reached terminal velocity. Okay, the student then measured the time taken for the ball bearing to fall 20 centimeters. A, give one other measurement needed to determine the viscosity of the oil. Okay, so in the Stokes law, right? F equals, I need to recall the formula there. 6 pi r nu v, and v is the terminal, nu is the viscosity. Actually, it's eta, not nu. Yeah, this is eta, the Greek letter, and r is the radius. Okay, so we have the time taken, and of course this F is the same as when it's terminal velocity. This is, so the ball is dropped, right? Yeah, so the only forces acting is the weight and upthrust. Hang on. Right, okay. I personally forgot the formula, but this is drag plus upthrust, which is rho g v, where v of the ball is just 4/3 pi cubed, yeah, equals the weight, which is rho g v as well, also weight of the ball. Oh, but the rho here is the density of the liquid. This is the volume of the ball. Yeah, the same volume here, volume of the ball, but this is the density of the liquid, but this is the density of the ball. So in order to determine when it's terminal, right? When it's terminal, this equation must be true. Student measured the time taken for 20 centimeters. So time taken t for under 20 centimeters, that would give that, well, that can find the acceleration. Is that any use? Acceleration, why do we need acceleration? Oh, stupid me. Okay. No. It's simpler than that. Okay. One measurement needed to determine the viscosity. Wait, no. Probably not. Funny, it's just 1 mark, but I'm not figuring it out here. Give one other measurement needed to determine the viscosity of the oil. So we want this thing, viscosity of the oil. Yeah, so student measuring 20 and the time taken here, that would allow calculation of VT, right? So that means we need to know the density. I mean, yeah, you would have to know, you would have to know a lot of things from my calculation here. So the radius of the ball, the density of the ball. Well, this thing is just the weight of the ball. But this is the, okay. What? Viscosity of the oil. You know, I would go with the radius of the ball, you know. Oh, he measured the diameter of the ball, so R is known. I didn't look at that, sorry. Okay, so G is known. Measure the diameter of the ball bearings of the ball. Measuring is in the visible oil as shown, is terminal velocity. I mean, we still need the density of the ball because we don't know the density of the liquid. This is oil, right? Okay. Yeah, I would go with the density of the liquid though, not the density of the ball, maybe. Yeah, I'm gonna go with density of the liquid. Density of oil. Yeah, this would be my answer here. Not sure there. The diameter of the ball was that, the time taken for was that, Susan calculated the value, that for the viscous drag. Oh, hang on. This might be a hint for the viscous drag of the ball bearing. Okay, so we're just going to do F equals 6 pi R nu Vt. And then, yeah, so that would be 5.6 times 10 to the minus 5 equals 6 pi. Well, I'm just going to move the equation already, yeah? So viscosity nu is just F divided by 6 pi R, which is 1.24 divided by 2 times 10 to the minus 3. That's just R. And then Vt, so Vt is just 20 divided by 1.3, so 20, well, 0.2, right? Because that must be in meter, divided by 1.3. Just gonna plug everything in there, yeah? Okay, so 5.6 times 10 to the minus 5. 6 pi times 1.24 divided by 2 times 10 to the minus 3, and then times 0.2 divided by 1.3. So that comes to be 0.031146, blah, blah, blah. I'm just going to make it 0.0311, okay? Like that. Okay, so that would be the answer there. Okay, so that means, yeah, the other, yeah, I think density of oil would be fair because it would allow you to find the force here. If we know the density here, we just plug it in there, and yeah, is that right? Yeah, I would say I'm gonna keep the answer like that. Student repeated the experiment. He used the same oil at a lower temperature. Explain how using oil at a lower temperature, affected the time taken for the ball bearing to fall. Right. So, I mean, if you lower temperature, so we're just gonna go with the logic there. At lower temp, viscosity, which is the new here, increases. It's gonna get more viscous. Yeah, the viscosity of the liquid of the oil will increase. So that would give you more drag. So drag increases. Yeah. That means the terminal velocity will be reached faster, right? So the terminal, right? Because if you have more drag, then it's like, imagine you drop a feather from the air, it's going to reach the terminal velocity faster than dropping a ball with the same size and same mass, because it's got greater surface area, so you get more drag. So the terminal velocity is reached sooner, right? When it is reached sooner, so the final terminal velocity, so therefore hence smaller. The terminal velocity would be smaller than before. Okay, when it's reached sooner and it's smaller, because it's going to increase from 0 to something. Okay, so that means the time taken, therefore the time taken to fall is greater. So if you imagine the dynamics of that, have a little imagination here. It's going to go like it's going to reach terminal velocity sooner, and it's going to keep going slow like that because it's so viscous. Yeah, okay, so that would be my logic there. That's it. Let's hurry up a bit. Number 17, we have a violin here. Is a musical instrument that has 4 strings as shown. A force extension graph for the sample of 1 string is shown below. Okay, we have a table here shows the stiffness for samples of 3 of the strings. On the violin, each sample was the same original length. Okay. Deduce which string used to obtain force extension graph. So we just basically need to find something called the stiffness here, which is just Newton per meter. So it's just probably the gradient of this graph, but with the right unit, because note that it's millimeter here, so it's the first thing you need to notice, the units of the graph. So I'm just going to find the gradient. Well, let's take 2 points very further away. So what do you see? I'm just going to take maybe this point right here. Yeah. And maybe further down, very down. I'm just going to go with this point right here. All right. Let's do a large triangle there. Is it that? That, right? Yeah. And then down here. Okay. So it's going to be, so the gradient of the graph here is, well, that is, this is 70, yeah? So that's, what again? 2 per square. So that would be 76 minus, down here we have 8, right? Divided by delta x. So this is 25. So what is that? It's just 1 per square, yeah? So that's easy. So that's 28 minus, and this is 3. But note that this is Newton. Well, this whole thing is, well, let's change it to meters already, yeah? So I'm just going to do times 10 to the minus 3, all right? So that is going to be 76 minus 8, So that's 25 times 10 to the minus 3. So 2720 Newton per meter here. Okay, and that would be the working there. And well, since 2720 Newton meter from the graph, this is the gradient of 2720 from the graph is closest to that the stiffness of string y. Yeah, therefore string y was used. Okay, here we go. B. The fourth string on the violin has the original length of that when tension applied to the string is 36. The new length of the string is that. Radius of the string is that. Determine Young modulus. Okay, so Young modulus E is just stress divided by strain. Stress is just force over extension. So 36 divided by extension, and extension, original length. So extension is 0.752 minus 0.750 because they give you the original length there and the new length. Oh wait, hang on. Extension, I must be, yeah. That should be area first, sorry. Extension is down there. So epsilon, which is the strain, is extension over original length. So this is the extension. Original length is 0.750. The area, cross-sectional area, is just pi times, well, that's the radius, so we're just going to do 0.85 times 10 to the minus 3. This is squared first, yeah. So that would be the Young modulus there. Just plug everything in again. Okay, so I'm just going to do 36 divided by, 36 divided by pi times brackets 0.85 10 to the minus 3, and then square that. That's the cross-sectional area. And then we're going to multiply, because we are moving the fraction here, this would be multiplied up. So I'm just going to be 0.75 here divided by the extension, which is 0.002, right? Just subtract that. So that's it. I mean, the number should be reasonable. In this case, I think it would be something like that, yeah. So that's about 5.947 blah 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 times 10 to the 1, 2, 3, 9, yeah. And this is Pascal. So 5.95 times 10 to the 9 Pascal. That makes sense. That's gigapascal. Okay, yeah. 5.95 times 10 to the 9 Pascal. Okay. Number 18. Okay, 18. Newton's cradle has 5 identical steel spheres. A to E, each sphere hangs on a string from the frame as shown. Each sphere has a radius of that. Calculate the mass of one sphere. Okay, that's fine. So mass is density times volume. So density is that times volume. Well, we have in meters already. So 4/3 times pi times radius cubed. Yeah, so that would be the volume. Okay, so 7.8, what's that? Times 10 to the 3, okay, times 4/3 times pi times, I'm just going to do 0.007 here, yeah, cubed, all right? So that would be equal to 0.011206 blah blah blah. Wait, this is the mass, right? Okay, mass of one sphere, yeah, 0.0112 kilograms. That should be SI unit. All right. Yep. Next, a student pulls a sphere A So the string is at an angle of that. Vertical shown, student then releases the sphere A. Direction of acceleration is that. Determine the initial acceleration of sphere A when released. Okay, so okay, so let's just do some force diagram here. So that's the tension and the weight is here when released, right? So the acceleration, right? Yeah, okay. So the resultant force acting on the sphere must be T plus W. I mean, if we consider like a vector diagram here, yeah. Let's see if we have to draw a vector diagram. Probably not. We already know the weight, right? We don't quite know the tension yet. But okay, we can solve the equation that this is 2 marks, all right. Okay, so this must be also 38. So this is then T cos 38 degrees. This is then T sine 38 degrees. Okay. Makes me wonder a little bit there, but oh, and this is in circular motion as well. Circular motion is not U1, is it? T cos theta should be W, no? It doesn't say that the diagram is drawn to scale or not. Should we take our chances? I mean, we could. No, we shouldn't. We shouldn't do that. Hang on. Right. Because, okay. So I'm just going to do, why is this a little complicated? AX and AY. So AX is just T sine 38 over M, where M is the mass, right? And AY is just W, which is mg, minus T cos 38 divided by M. And to find the initial acceleration, we should do Pythagoras there, right? Yeah, because the resultant force to the right is just T sine 38. The resultant force vertical is weight minus the tension, like that. Wait, hang on. I should divide overall by M like this, not, yeah. Okay, so we're just going to try this. T squared sine squared 38 divided by M squared. I believe it's probably going to give me something. Okay, and then, well, let's just simplify that. So we get G minus T cos 38 divided by M. Whoops. And then we have plus here. Ooh, this is horrible. We need to square that, right? Am I over complicating it? Wait, isn't this the same? No, it's not. Initial acceleration of sphere A when released. When released. Oh, hang on. I think I'm over complicating it. So when released, the ball must go down, but we don't know the tension. The ball must go down. Shall we do acceleration? Shall we do like this? Hang on. I'm just going to take my chances here. I always do that. This is 38, so that means this is also 38, right? We know that there is a component of vertical here, and I'm just gonna say that it should be the G. Yeah, I mean that should be G. So if we do triangle here, so this is also 38. This is the acceleration we want, but the vertical component is 9.81, right? So 9.81 divided by the A we want would be equal to sine 38. I'm just going to do that maybe. Okay, so A would be 9.81 divided by sine, this is radian, let's change it to degree, 38. Yeah, I'm just going with 15.9, all right? Yeah. Okay. Yeah, all right, anyway. Maybe I'm not too convinced with that, but that's the best shot I can give you. Yeah. Diagram 1 shows the position of sphere when the... Can I just check how many questions left? Oh, quite some question. Am I going to make it? Let's see. Describe the changes in energy and momentum of spheres A and E. This is 6 marker. From the time sphere A is released until the sphere E reaches the highest point. Okay. B the address, sphere E moves away from D, moves away, okay. Okay, so energy and momentum of sphere A and E. Okay. From the time sphere A release until the sphere E reaches the highest. Okay. When A is released, okay, GPE transfers to KE. Yeah. Where there is a maximum speed there of A. A then collides B, okay? And when A collides B, we have momentum to conserve. So when A collides B, it's going to transfer the momentum all the way, yeah, from A to B, from B to C, C to D, and D to E, okay? So because A will not fly off, right, after bouncing with B. So as A doesn't rebound, so the momentum as must be conserved will entirely transfer to B and to C and so on to E. Okay? As A, B, C, and D don't move, the energy, the kinetic energy gain by E is equal to that of A when A hits B, assuming no energy lost to surrounding. Yeah, and so yeah, and then E will, and then for E, yeah, KE will transfer to GPE as it rises. Yeah, as it rises. Reaching the height, reaching the same height as A when A was released. Yeah, that would be how I put this in totality there. Well, that makes me think, okay, I mean, I still don't like this one, but okay, I think I gotta go with that. Don't have much time. Number 19, okay guys. Student stores a bicycle on a rack. The bicycle rests on the rail that can rotate about the pivot. To take the bicycle off the rack, the student uses a handle to lower one end of the rail, like that. The piston applies a force to the rail as the rail is lowered to the ground. I'm thinking of moment now. Okay. The diagram shows the bicycle on the rack before and after the rail has been lowered to the ground. The piston applies a force to the rail. Okay, like moving down. Yeah. Okay. When the rail is in equilibrium, the principle of moments applies. The state what is meant by principle of moments. Okay. So total clockwise moments equals total anti-clockwise moments. I'm just going to make it short, yeah? Okay. After taking the bicycle off the rack, the student lifts the rail back to its original position. Wait, hang on. Okay, that's the... Oh, you can see the question here as well. Okay. The uniform rail has a length of 1.4 and a weight of that. Student applies a force F to the handle perpendicular to the rail. The piston applies a force of 160 newtons to the rail. Diagram shows this force acting on the rail. Determine the minimum value of force F needed to lift the end of the rail off the ground. Well, that's just moment, right? Okay, so sigma m equals 0. That's the total moment equals 0. So we have clockwise equals anti-clockwise. Well, anti-clockwise equals clockwise there. So I'm just going to do F times the length, okay, 1.4. And is that the only anti-clockwise? No, there's this one as well. So we're just going to do, find the component of that force, which is 160 sine 18, right? Yeah. And the other component doesn't do much because we're going to take this as a pivot. So that would be plus 160 sine 18 degrees. Well, because the lever arm here is 0.37, so I'm just going to put it there. And the clockwise moment, the only one is just this guy. So I'm just going to do this perpendicular distance like this. Because the weight is at the center, this is a uniform rail. So that would be, this length is 0.7 here. So it's going to be 0.7. Well, you resolve that down. So it's cos 42 multiplied with the perpendicular force, which is 95. Okay. So that would be everything I need to do. Just calculator. So I'm just going to do 0.7 times, well, I'm just going to do fraction already because I have to divide at the end, times, this is in degrees, so cos 42 times 95. I got to do minus 160, move to the right hand side, sine 18 Yeah, okay. Times 0.37 divided by 1.4. So that would be the answer. Okay, I'm just going to do 3 sig fig there. Okay? Alright, so next one. Student could have lifted the rail by applying a vertical upward force to the handle. Wait, where's the handle? Okay, the handle of the bicycle. The force needed to lift the rail is different when the force is vertical compared with the force that is perpendicular to the rail. Okay, yeah, that's a okay. Explain how the minimum vertical force needed is different. You do not need to include any further calculation. Wait, where's the handle? To the handle. So the handle, we need to find where the handle is. Handle. The student uses a handle to lower one end of the rail to the ground. Oh, this is the handle? Oh yeah. This is the handle, I guess. Right? Or is it the handle of the bicycle? I'm not sure now. To applying the vertical upward force to the handle. Could have lifted the rail by applying a vertical upward force to the handle. I mean, that's not possible to lift the handle of the bicycle, so it must be the handle of the piston, I think. Right, don't you think? Yeah. So, okay. So I would say applying a force at the handle would have a smaller lever arm, yeah, from the pivot, right? Hang on, let me just 160 is the bicycle. The piston applies the force. Yeah. Smaller lever arm from the pivot compared to then that by force F. As other forces don't change, the clockwise moments are the same. Therefore, because we have smaller lever arm, so we would need greater force, right, to produce the same anti-clockwise moment. He would need a larger force than F as a minimum. Yeah, so you would apply greater force than before, all right, because the moment has to be the same. Okay, 20. I don't think I'm going to make it. Actually, I have to leave early as well, although I have 13 minutes. I think I might well finish. Oh, it's the last question. Okay, let's see. Skydiver jumped from an aeroplane. The initial vertical velocity of the skydiver was 0 during the first 1.5. Skydiver moved vertical distance of 11. Air resistance ignored. Negative if the mean acceleration. Deduce whether air resistance acting on the skydiver was negligible during the first 5. Okay. So we can calculate the acceleration here using just suvat v squared equals u squared. Is it? Vertical distance of 11. No, it's initial velocity. Okay, s equals ut plus half at squared. So 11 equals 0 plus 1 half a 1.5 squared. So we're just going to solve for a and see what happens there. So that's 11 times 2 divided by 1.5 squared. That's 9.77 ... And then if we divide by the g, yeah, if we divide this by 9.81, it is equal to 0.996. So a is 0.99. I'm just going to make it 7 g, which is greater than 0.95 g. So maybe considered negligible if the mean acceleration of the skydiver is greater than that. Yes, can ignore because we have greater, yeah? Ignore air resistance. That makes sense. Next, the displacement time graph of the skydiver between the jumping from the aeroplane. I'm going to have a second to tell someone that I'm going to be late, right? Okay, because I'm going to have to finish this paper. Actually, I have an appointment in 2 minutes, but it's okay. I'm just going to... Okay, yeah, let's finish this once and for all. We have displacement time graph of the skydiver between the jumping from the aeroplane to the opening of the parachute, and then sketch the velocity time graph on the axis below for the skydiver between jumping from the aeroplane, of course. Okay, so we're going to make the time correspond here. So let's have the vertical line here, yeah. That's where it ends. So, right, so it's diving down. The vertical velocity should also be negative then, right? Yeah. But okay. So vertical velocity would start at 0, right? And then as we know, velocity is the gradient of the graph. So at first, velocity is 0 because the gradient is 0. And then assuming that this is, of course, a free fall because we ignore air resistance. So that means this must be a straight line. Yeah, like that. But we can calculate, yeah. So 11 vertical distance. Yeah, I'm just gonna do this. Look. Okay, so I'm just gonna do this, and then we're gonna say that this. Well, we can do some tricks here because we know that the distance fallen is 11, right? So the distance fallen is going to be this area. It's kind of like under the graph, but it's not exactly physically under, but we call that under the graph, right? So I'm just going to do half times base, which is how many seconds here? Oh, wait, no. Oh, hang on. During the first... Okay, right. No, I think that's fine. We can calculate by ourselves. This is just to know that this is 21, right? Yeah, it's fine. We can find the velocity, v equals u plus at, because u is 0 and a is just going to be accurate, right? So we're going to take this guy, yeah, 0.9, wait, that's 0.9. I should have got this more accurately, right? Hang on. Yeah, let's do that. Yeah, so that is the actual acceleration. So if we multiply that by t, which is 21, isn't it? Yeah. It's going to be 205. Wow. Yeah. So that's 205.3. So I'm just going to put 205 here. Negative 205. Okay. All right. Yeah, it's a straight line and up to that. Okay. After jumping from the aeroplane, the skydiver accelerated and then reached the terminal velocity before opening his parachute. Okay. Wait, hang on. After jumping from an aeroplane, the skydiver accelerated and then reached a terminal velocity before reaching his parachute. That's weird. If mean acceleration of the skydiver is greater than 0 point. That is greater, right? Yeah, we got it greater. Okay. Yeah, is it? Okay, right. The drag gets larger and larger when he falls down, right? Yeah, okay. Explain how energy conservation applies to the skydiver before opening his parachute. Okay. As he falls, GPE transfers to KE, yeah, then reach a terminal velocity. Okay. And as well as, well, just gonna write and heat to surroundings. Yeah, due to friction, due to air resistance of air. Oh, air resistance of air, that's weird. Okay. And is that it? GVE transfer to KE and heat due to surrounding. And then before opening his parachute, as he speeds up, right, there is a greater air resistance. So the rate of transfer of energy to surrounding as heat is greater. Yeah, until at terminal, which is at the point of opening the parachute, there is at terminal and beyond. Well, we're just going to say beyond, the KE doesn't change. And KE doesn't change because it's at a constant speed. So the GPE lost will transfer to heat due to air resistance. Yeah, so that would be it. Okay. And the last one, 3 minutes. The skydiver opened his parachute and his speed changed after a time. He reached the terminal velocity. Yeah, the second one. Explain how the forces on the skydiver cause his acceleration to vary after his parachute opened. Okay. So when we have a parachute here, right? That's a parachute. After open, once opened, there is initially a large extra drag force. Okay, leading to upward, resultant upward acceleration. Thus, downward speed decreases because you are accelerating upwards, right? But you're going down. Therefore, drag decreases as you go slower. Yeah. The total, well, weight and as weight is the same, but drag decreases, so total upward resultant force decreases, therefore acceleration downwards, acceleration upwards decreases until forces are balanced. Resultant force equals 0, so acceleration equals 0, another terminal velocity. I just made it. So I think I'm going to go with that, guys, and that's the end. I'm going to mark the paper in a bit. See you. Okay, guys, this is the mark scheme, the official mark scheme of the paper. Let's see how well I did. Let's start from the multiple choice section first. Okay, so number 1, D, great. Number 2, A. Number 3, B. Number 4, C. Number 5, B. Number 6, B. Number 7, D. Number 8, C, 9A, and 10A. Okay, so I nailed the multiple choice section. Okay, although I could have flopped some of them because I mean, it was I got started a bit rough here on the first question, taking a bit longer, and then number 11, yeah. So number 11 here. Well, let's hang on. Let's make that a little more proper there. So, okay, here we go. So number 11, yeah, 152, yeah, that should be fine. Number 12, displacement is a straight line, so I'm just gonna underline, yeah, that, because it covers what it says there from start to end. Distance is the length of the part, so distance is a scalar. Run from, okay, the path shown. So the actual distance traveled is greater. Yeah, I think I'm gonna give my mark that. Give the mark to that part because I already mentioned that distance is a straight line and it's the actual distance traveled here would be the path. It's not a straight line. Yeah. I mean, some people might not give me the mark, but okay. Let's see. Allow distance is not a straight line. Yeah. Okay. There is additional guidance here. Yeah. So I should get all the marks there. All right. So when I have the mark scheme, I'm just gonna mark to show you how I score myself as well. Yeah. Just to be fair there. 12B. Determine the maximum acceleration. Yeah, this one. Yeah, 0.27. So that should be fine. Just find the gradient and everything. Number 13. Delta S is 1.1. Yeah, I got that part right. And then I showed that it was actually 2.8. So it's no. Okay. That's fine. Haven't lost any mark yet. Good. So number 4. Yeah. Efficiency 28%, or I got 27.6, which rounded to 28 indeed. Yeah, I did use of kinetic energy and GPE, and I find delta. Yeah, so let's see the numbers here. Total, wait, hang on. Yeah, this part here. The denominator of this part is exactly the same as what I had here. Yeah, and that would have converted to still the same number. All right, so that's fine. 15A, this one, compression. So, I got a different number. Okay. 60 to 97.5. That's nasty. How do they, wait. How do they count that? Hang on. That's 37.5. 85, right? 85 is here, isn't it? That should be halfway here, and 140 is there. That should be also here. How they got that accurate? Okay, so I would probably lose the accuracy mark here. Okay, allow compression changes from 55 and 62 to a value between 95 nanometers and 100. So what did we get again? So hang on, we did, I would have read that as, this is 57.5, right? And that would have been 97.5. That's why I got 40. So yeah, they allow this is 55. Between 55 and 62, I got 57.5, so that's fine. And the other one, 97.5, so that would have been fine. Yeah. So I indicated in the graph there, but I didn't quite show the number here. Yeah, maybe that's where I lost mark. Okay, I'm just going to be harsh here because I don't show that this is 97.5 minus 57.5. So because I counted the squares. Okay, I'm just going to take one mark away. But I think I got the right answer here because they allow the compression between those range. Yeah. Okay. This is just an example calculation, right? So if I took exactly 57.5 and 97.5, which they allow that, so the answer should still be in the tolerance range. Yeah. Okay. Part B returns to original size when the force is removed. Yeah, that's right. Okay. Number 16, mass of the ball bearing. What? Allow weight of the ball bearing. Ignore density. Allow density of oil. Yes, got it. I got that one then. Almost. Okay, yeah, there are a lot of things you need to know, right? Like, I would say, yeah, like the density of the oil, like the mass of the oil, because you don't know the density of the ball. Oh, that doesn't allow. Okay, all right. But anyway, okay. 0.031 Pascal seconds. Yeah, okay, that's right. Part C, greater viscosity. Viscosity increases here, I got it. So the ball falls as a smaller terminal velocity. Smaller, yeah, I got that point. And then time taken greater. Nailed it. Okay. That is the groove. Okay. Yeah, I got the gradient to be similar value there. Maybe just the reading, plus or minus error there. So I think that's fine. And so the answer is Y. Yeah, that's fine. 7B. 6 gigapascals. Yeah, that's about 6. Yep, that's right. 18. 1.1 10 to the minus 2. This is 1.1 10 to the minus 2. Yeah. Okay. Yeah, this one, I don't know. So this one, I took so long for this one and couldn't figure it out because I got it wrong here. Yeah, use appropriate trigonometry. It says that. Initial acceleration is 6. Right, so what did I do wrong here? Resultant force is MA sine. So I guess, yeah, I got 0 here. Right? And that's not appropriate trigonometry either, the way I did it. So I'm just going to mark myself down there. Okay, this 6 marker here. All right. Okay, so as A falls, GPE transferred to KE. Yeah, that's perfectly fine. You can say A GPE decreases while KE increases, or you can say GPE transfers to KE. Yeah, I got the first point there. Momentum of A increases. I didn't say that, did I? I just say that A had some momentum. Yeah. A doesn't rebound, so the momentum, as must be conserved, will entirely transfer to B. I didn't say that, so I missed one mark there. Momentum of A decrease as momentum of E increase, or during collision momentum conserve. Yeah, I said that. So energy of A is transferred to E. Energy of A transferred to E. I think I said it indirectly here, but I just say that as A, B, C, D don't move, the KE gained by E is equal to that of A when A hits B. Yeah, that's just to say 0.4 here, yeah. As E moves, both kinetic energy and momentum decrease to 0, and gravitational potential energy increases. Yeah, I didn't say about the momentum there. Assuming no energy loss. Okay. For E, KE will transfer to GPE as it rises. Yeah, I didn't quite say the momentum. I forgot because they say that I need to speak in terms of energy and momentum there. Right. So I have one mark here down for 0.5. I didn't cover that. So if I have the total energy of A before collision is equal to the total energy of B after collision. Final gravitational potential is the same as total energy remain same throughout. Hang on. Reaching the same height as A when A was released. Didn't say any of that. Or did I just get it before? Total energy of A before collision is equal to total energy of E after collision. Maybe not. That's bad. I lost 3 marks. Alright, so what did I get here? If I have 3 points, max final mark, I see I mark 2, final, okay, the linkage mark here, I need to use my consideration. I think everything is fine. I wrote in the flow here. Answer is partially structured with some linkage lines reasoning. Yeah. So I'm gonna mark myself 3 here. Yeah, for this one. So I lost 3. Bad. It's just that, I forgot to mention about momentum. Right? Yeah, which is half the story there. Okay, this one. Yeah, total clockwise equal anti-clockwise. That's fine. This one, 22.2. Yeah, should be fine. Next. Okay, so it's a larger force. Yeah, I got this fine. The last point there. The same force is applied vertically. Hang on. Same moment about the pivot. Okay, yeah, I think I wrote same moment there. Yeah, same anti-clockwise moment. And then force is applied vertically. The moment of the force is less. Perpendicular distance from the line is less. Yeah, I think I covered that one. Like the lever arm here is smaller. Yeah, the handle would have a smaller lever arm. There you go. Okay. And then we got here to be 997. Yeah, that's greater. So air resistance negligible in that case. Wait, what? I got this line wrong. Displacement velocity. Oh, okay, because it was only straight line at the very beginning. Yeah, it was only straight line here. Yeah, I forgot about terminal velocity. So although there was terminal velocity, but I didn't think of the line that it should be that. Bad. Yeah, it should be a curve. Okay, so how many marks do I get here in part B? Curved line starting at 0 with negative gradient decreasing in magnitude. Nope. Horizontal line after 12 seconds. I got 0. Alright. Fine. As he falls, GPE transfer to KE. Yep. While accelerating, KE. Oh, I didn't write this second point. While accelerating. Okay, this is about energy. Okay. Oh, as he speeds up. Hang on. As he speeds up, greater air resistance. Now, the rate of transfer of energy to the surrounding is greater. Oh, and work is done against air resistance. Yeah, I said that, right? Yeah. Well, and energy dissipated due to air resistance at terminal velocity or delta E gravitational is dissipated due to work done. Well, I think I said that. Wait, hang on, why is there an or here? Okay, I didn't say this. While accelerating, EK increases. I only say he speeds up, but not saying EK. Right, so I'm gonna lose one mark there. And work is done against air resistance. I said that, right? Yeah. So I covered that. Yeah, energy dissipated due to heat, yeah. And then terminal velocity. Yep, I also covered that at terminal, KE doesn't change to GBE. KE doesn't change, and GBE will transfer to heat due to air resistance. Yep, so I lost one mark for that. And the last one, explain the forces on the skydiver. Yeah, when he opens the parachute. After he opens the parachute, air resistance greater than weight, resultant force upwards. Yeah. Yep. Allow drag for air resistance throughout. Yep. Okay. And then, well, I didn't quite say air resistance greater than weight. I only say that there is a resultant force upwards. Yeah, I only covered half the point there, so I minus 1 here for the first one. And then the second point I said, yeah, resultant force upwards, so I have the second point. As speed decreases, air resistance decreases, yeah, that decreases there. And then upthrust plus air resistance equal weight, so that is at terminal. Until forces are balanced, yeah. You see, I didn't say exactly that air resistance equals weight. Okay, I should mention all those names. Right, so I minus 1 again. And yeah, I said the last thing here about resultant force and acceleration. So I lost 2 marks, that's bad. Okay, let's count how many marks I got here. Minus 2, minus 3, minus 5. Minus 5, minus 8, minus 10. Right, yeah, I think just minus 10. That's not too good. Oh, minus 11. Oh my god. Yeah, I think that's it. So minus 11 out of, yeah, that's 69 out of 80. I mean, could have been better if I were more careful. Yeah, spent a lot of time on some questions, particularly the trigonometry one that is just the acceleration. Let's do a review, yeah, on the whole paper. So multiple choice question could have been tricky, but mostly they are easy. You got to be careful because some of them might just trick you into thinking very long, but actually they are not that bad, right? Like you know, the first one I almost flopped there. This one, yeah, the diagram looks a bit weird because they're not drawn from the same point, but this is from the back of the picture basically, and they have a hook there and the string, so you need to know how that works. And yeah, this one, constant acceleration is the key there. If acceleration is constant, then displacement should be a curve because velocity is a straight line. This one is fine, you just need to do Pythagoras, yeah. Everything else fine. Oh, this one, yeah, I spent quite some time on number 9 as well. Almost didn't get it, but yeah. P equals FV, and the V average, because it's average power, so it must come from average speed. Average speed in SUVAT is just U plus V over 2 because we assume that acceleration is a constant value. Okay? That's why we can work it on like that. And this one, yeah, just momentum. So yeah, number 11 is fine. I think most of you should get that. This one, just be thorough about how you explain. When you see a question like this, you might think that, yeah, displacement is a vector, you know, because it doesn't say in the question. You should not assume that what you know is not what they expect. Sometimes what you know is what they expect, right? like in the parachute question, I didn't write about weight, right? So I didn't write about weight equals air resistance because I assumed that by writing resultant force being 0, I would implicitly mean that weight equals air resistance, but you just need to be explicit, mostly in a physics paper. Yeah. Okay. And again, this is my first walkthrough on this, on the physics paper. Yeah, should be more fun than math, I think. This one is fine. Just pick the steepest gradient, right? Yeah. Yeah, this one, right? I mean, if you use Suvat, would it have worked? Well, yeah, you would have got the distance traveled there, which is 1 point. Yeah, you could have done like, oh yeah, like this, right? And then you would have found S, and then that would also work. Yeah, I think so. Yeah, that would have worked. Yeah, could have done that, but yeah, that's the idea. So you pick the first point and the final point, so, and calculate the distance to show that it's not the case. Yeah, this one, some conceptual thinking here about energy, because some kinetic energy have to lose to GPE gain. Yeah, but the other part is just going to be the total energy that is possible to be converted to something else that is not GPE. So that's why I took this as the overall, like the total possible input, and calculate the efficiency like that. So this one is it's like a good example of how, of a question to test how you understand energy conservation. Yeah. Yeah, this one is just 15 here is energy, elastic potential energy stored in the material when it compresses or stretches. Yeah. And because I wasn't too thorough there on the numbers, I mean, I kind of had that in mind, but I just, okay, this would have been fine because it's obvious that we would find the difference. Again, I assume that they would know how I got 40 here, or I assume that they would be okay if I wrote it, if I do on the graph like this. I mean, some examiner might be okay, but I think mostly not. Yeah. So that's why I took 1 mark away. But though I get the final answer right, I kind of show the working here, so it should be fine for the final mark. And number 16, yeah, spent too long thinking about the other measurement that would be needed to be determined. Yeah, in fact, it just the density of oil. That would be the best one, I would say, or the mass of the ball. You can't really, okay, the fact that they don't allow density here, let me go to that one. Which one is that? 16. The fact that they don't allow density here, I just happen to have an idea here. Because how would you measure the density of the ball? You would need to measure the mass and the volume, right? Because they already covered the diameter here. That means you need the mass. You can't directly measure the density of the ball. You would need the mass and the volume anyway. So that's why they accept mass, but not the density of the ball. Yeah? Okay? So, but I was lucky I got density of oil there, so it was correct. There you go, yeah. And then, yeah, calculate the viscous force here is fine because we use Stokes' theorem there. And this one is fine, yeah. So temperature and viscosity are, related to each other, okay? This one, yeah, still okay, right? Young's modulus, and calculate the gradient to be the stiffness. So I'm just going to skip this one. Yeah, you have to know how to use this formula properly. And it's just you having to be careful with the units here, nothing else. Yeah, the explanation, okay, this one, yeah. The concept is about energy. Okay. You might be thinking there is a string. Why does it not change the energy of the ball as it moves down? Kind of also down here. Well, think about it. Tension here acting on the ball perpendicular to the motion of the ball. So this is, of course, circular motion. Right? This is circular motion. Now, because the force of tension is perpendicular to the motion, because direction of acceleration is also the direction of motion there. That means during the motion, the force due to tension does no work on the ball. It does no work because the force is perpendicular to the motion. And we know that from the definition of work done, if F and S are perpendicular, then there's no work done. Right? That means there is no effects from the tension on the energy of the ball. So if you drop the ball from here, and let's say we draw a horizontal line. So by the time that the ball swings down to here in a swing, or in the case where you drop the ball, falling from that point to the same vertical height there down, they would have the same kinetic energy. So there is no change in kinetic energy. I mean, there is no change in the dynamics of the kinetic energy. I'm just saying that the ball from here to here would take the same time as the ball from here to here. Okay? Well, if they take the same time in that vertical distance, it means that the vertical acceleration must be the same. Right? Because only by having a swing like that, using the tension of the rope to tie it to a circular motion, it doesn't mean that it would change the dynamic of the energy transfer there. So because the vertical acceleration is the same, then so rather than doing that, the acceleration due to gravity is the hypotenuse. Actually, that is the net acceleration, the resultant acceleration. That's why they're doing. So multiply 9.81 by sine 38 is to find the component. So one component here, and there should be the other component here. If that's 38, this is 38. So this is also 38. Yeah. That's what they do. So they just resolve this acceleration into this. So the other component should be that. And that is it, guys. That's neat, I would say. This one is neat. I like this one, actually. Although I lost marks for this one, but I like it. Yeah, okay. Makes me think quite a lot there. Anyway, yeah, this one I just forgot to write about momentum in most of the parts there, so I lost 50%. I'm just going to be harsh here. Yeah, I might get 4. I don't know. If I were lucky here, I would get 4 maybe. But I'm just going to be harsh here. Yeah, don't forget to cover, like if they ask you to speak in terms of energy and momentum, it is, you can maybe assume that they split the marks in half, right? They share half for the whole marks. So when you say about energy, don't forget about momentum. So so at first A has 0 momentum, and then when it hits B, as it falls, momentum increase, KE increase as well, something like that, right? So yeah, I just rushed too much on that, so I didn't answer that properly. This one is fine, principle of moment. So yeah, moment calculation, no worries here. Just don't get confused about the distance on the lever arm there. Yeah. This is obvious. You have smaller lever arms, so you have to produce more force to give the same moment, right? Okay, this is skydiver. Yeah, Suvat. The first part was fine, Suvat, straight, but this one I missed this. So it should be like this. It should be like a straight line at first, because at first, I mean, the reason why they give you this example, because 11 meters from the point of release, there is no air resistance, presumably, because we proved in the first question here that for small distance fallen, air resistance can be ignored. So it's still a straight line down here, but then later on you're going to have like a curve, which plateaus to be a terminal velocity. Didn't get any mark there. I didn't think of that. Yeah. And then this part, yeah, I covered most of them, but I lost 1 mark here for not saying KE increases. I only said speeds up, but didn't say about kinetic energy again, because they mentioned energy conservation, so energy is the key word. Any energy change should be mentioned. Didn't put that in, so I lost 1 mark. Just being harsh. This one lost 2 marks. Yeah. I didn't say, yeah, so when I say forces balance here, I should have said weight equals drag. And then, yeah, this one, I only said large extra drag, but I should have said drag greater than weight. You see, I assume that by saying large drag, anyone would understand that drag greater than weight. But no, you have to be explicit in physics. That's the nature of the paper. Okay, so I would say not too hard, but I didn't do that well. I mean, if I were to have any excuse, it will only be this is my first paper in this channel. All right, and I hope that was all useful, guys. If you are also doing maths, which of course you probably do, don't forget to check out the papers that I walked through already in the channel. And there's more to come on physics here. Just you wait, all right? I'll see you in the next one. Bye.